Alright, in this collection of videos we're going to talk about something called equilibrium. To understand equilibrium you have to have a certain amount of background knowledge. This slide is supposed to help you get some of that background knowledge. This is just some pretend reaction. Chemical A turns into chemical B. The stuff on the left side of the arrow, in this case it would just be A, that's called a reactant. That word is going to show up every once in a while. Stuff on the right side of the arrow, in this case that's just B, that's called a product. So in our pretend chemical reaction, A is the reactant, B is a product. You can have reactions with more, you can have chemical reactions with more than one reactant. You can have chemical reactions with more than one product, but this one is pretty simple. Not sure when we talked about this last, but I want to talk about something called exothermic and endothermic reactions. Exothermic reactions are reactions that produce heat. So exo kind of means outside of, and thermic means heat. So exothermic reactions are reactions that release heat or energy to the outside world. So if you see a chemical reaction like this up here, it says plus heat on the right side of the arrow, or it says A turns into B plus energy on the right side of the arrow. This stuff is also a product, which means this chemical reaction produces heat, or this chemical reaction releases energy. And if there is heat or energy on the right side of the arrow, that kind of reaction is called an exothermic reaction. And we're going to talk about that in at least one of the videos. Endothermic reactions are the opposite of exothermic. Endo basically means inside of, and thermic again means heat. And so endothermic reactions are when heat or energy goes inside of one of the molecules. You can think of it that way. But basically, endothermic reactions will have heat or energy written on the left side of the arrow. So if you saw a reaction like this, where heat or energy was on the left side of the arrow, that means heat is a reactant, and that means that reaction is endothermic. Heat goes from the outside world into molecule A, and it turns it into molecule B. This is a little bit more of a review. We're still going to keep talking about our simple pretend reaction. And what it says here is reactions don't necessarily go to completion. What I mean by that is, imagine that you have a test tube. Here's my test tube. And it has a bunch of A molecules bouncing around in it. If you're a beginning chemistry student, most times chemistry students feel like if you wait around long enough, I'm going to draw a clock here. There's my clock. If you wait around a long enough amount of time, all of the A's will turn into B's. And if that was the case, then you would say the reaction goes to completion. But most reactions don't necessarily go to completion. In other words, if you waited around long enough, not all of the A's would turn into B's. So let me show you an example of that. So this is maybe a more realistic example of what happens in the real world. Let's say that I have a whole bunch of A's in my test tube. I wait around an hour, I come back later, and one of my A's has turned into a B. That's a B there. Wait around another hour, and another one of my A's turned into a B. So now I have 2 A's and 2 B's in my test tube. Wait around another hour, and maybe another one of the A's turned into a B. Now I have only 1 A. Here it is up here. And I've got 3 B's. And I wait around maybe 10 years now. I come back later, and it's still the same. I have 1 A, and I have 3. This is a more realistic example of what happens in a lot of chemical reactions. In other words, this reaction doesn't go to completion. I don't convert all of the A's into B's. It doesn't have, in this case, once the reaction kind of stops, and you'll see it doesn't really stop. In this case, once the reaction sort of kind of stops, you'll say that you have 25% A's, 75% B's. It doesn't have to be these percentages. So different chemical reactions will end up with different amounts of reactants and different amounts of products when they kind of stall out. The other thing I want to point out here is that drawing a two-way arrow is a more realistic example of what's happening because A can turn into B, but the reaction can also run backwards and B can be converted back into A. So as another example, it could be that the ending percentages are 10% A, 90% B. It doesn't have to be 25%, 75%. These are just numbers that I'm making up. Could be 25%, 75% like I said. It could even be 85% A and only 15% B. But eventually, if you let the reaction sort of do what it's going to do, eventually the percentages will stop changing. Once you reach a situation where the percentages stop changing, there's a fancy chemistry term for this. You say that your reaction is at equilibrium. And we are going to talk an awful lot about equilibrium. One thing that I want to point out, however, is that let's say that this is equilibrium, where you have 25% A's and 75% B's. So let's just pretend that that's equilibrium. If you didn't know any better, you might think that nothing is happening here. That every time you look at the test tube, well, it's still 25% A's, 75% B's, nothing's really happening. But there is actually stuff happening under the hood, as I say. What's happening is that every once in a while, even when you're at equilibrium, an A molecule might turn into a B molecule. But if that's true, it's also equally likely that a B molecule will turn back into an A molecule. And so if that's happening, if both things are happening at the same sort of frequency, then the percentages aren't going to change anymore, even though things are switching back and forth. So that's an introduction to equilibrium, and that's probably enough background information to get you to where we need to go. So see you in the next video.
Miss